Okay, minasan, konnichiwa, Zamurai Engineer. Okay, let's discuss next chapter about design of tension members. But before we do that, please confirm our sound check. Sound check, anybody? Okay, thank you. Shout out, Zairine. So let us proceed with the discussion. So last live stream, we finished chapter 3. In fact, we have problem solving activity. If you can notice, however, the title of chapter 3 is Analysis of Tension Member. So in this chapter, it is similar with that chapter because we will be using the same equation, we will be using the same concept. However, the solution would be reverse. Okay? So instead of finding out the capacity of the material, instead of finding out the design strength, instead of finding out the allowable strength, so we are actually given those values. The problem will be given to us, particularly allowable strength. We have the given design strength. Now, we are going to find out what would be the dimension of the component of the structural element that would satisfy those design strength and allowable strength. So you'll notice that the procedure would be reversed. Actually, the same procedure, but reversed. For example, we have 4-step process in analysis of tension member. The same 4-step process, but we will start from the bottom going up because we will be solving for the dimension. Okay. However, we will still tackle some of the important concepts in design tension members that are not in any way discussed in the analysis of members. So there are still some concepts that we will have to look into. Okay, like what are the possible ratio of length or height and width of the member. So we have to discuss those. Those are important concepts and they are practical, meaning we could use them in our engineering work and our actual practice. Okay? So let us proceed, therefore, with the selection of section. Okay? So we will not explain it if ever we already have it. For example, this one, we already have this. Okay? So we already know that. We already know the effective area, how to compute gross area, how to compute net area, how to compute. Okay? So we'll just jump into those same concepts. Okay? For example, here, we already know this thing. So instead of finding out the ultimate, we are going to find out the gross area. Okay? So the process is now reverse. So let us move on faster. So we have what? Minimum, so that we have the dimension with minimum capability. Right? So same is true with ASD. So LRFD, ASD, it is just the same. Okay. So still the same with our previous discussion about uh, the service load. Okay, service load and the allowable load. Okay. So these are similar. So therefore, since there are no extra concept, so we will not deal with this. You can solve this using the same concept that we already learned. We will jump over this. We will jump over this. So take note. After design process, you will have to check. In the checking, it's the same process that we are already doing in chapter 3. So the same process. Same process. Now, new concept. This is a new concept. Slenderness ratio. Okay? So, this is the first time we are going to do this. What is slenderness ratio? Okay? Ly over Ry. So, Y meaning axis. No? So, length over radius of gyration. R is radius of gyration. I already explained it on the last live stream. So what is a radius of gyration? You can solve it by equal to square root of I over A. So that is our concept for R. Okay, so R. So therefore, you will have here minimum R. Okay. So, for example, L over 300. Okay. Okay, so we have here. No? So, if you plug in the given data, so 1.2 inches. Okay. And you have what? Minimum is equal to Ry is equal to 1.54. Okay. So it is okay because it is less than the value for the radius of gyration of the given element W12 by 35. Okay. So here. Ry is equal to 1.54. You can see this. You can take this out from tabulated value. Okay. So, for example, let us look at W12 by 35. So let us go to the W12 by 35. So W12 by 35. So here, so about here. So this W12 by 35. So these are the properties. Now take a look at 35. So 35 pounds per foot. So therefore, we have here the value 35 here 35. This is 35 pounds per foot. Look at the value of R 5.25 for x-axis and 1.54 for y-axis. That's why Ry is being referred to as equal to 1.54. Okay? So we are able to confirm the value. And we computed that the minimum is 1.2. So therefore, it is okay. This element can support, okay, the load of the given problem. So again, what is the load given from this problem? So the load is 110 kips live load and 130 kips dead load. So this combination of loads could be supported properly by use of W12 by 35. Okay? So that is what we mean by this. Okay? So let's move on to the next. So number 2, we are going to design 9-foot single angle tension member. So usually, since it is now a design process rather than analysis solution, analytical solution, so we are given what? Okay, we are given 9-foot. We are given the length of the beam. Okay, length of the beam. So, and then we have the working load. Okay? Working load. Working load is also referred to as service load. 40 kips live load and 30 kips dead load. Okay. So here. So tension member. Okay, here. So if ever we have the combination of load for both type of design methods. So very clearly we have the following. For example, minimum R. We have to determine the minimum R and compare this to the R value that you can find in the table, and look at the R value which is higher than this, and those are the type of elements that could be used, okay, to support this given combination of loads. So therefore you can find out that there are several types of elements that could satisfy this minimum R. That is the only thing. That is the only thing that would be different. Okay, would be different from the chapter 3. Okay, so we are confronted, for example, with so many things. So these are the values of R. They are all greater than the computed minimum R. So they are all possible solution. So you are just going to select. For example, selecting this one. Why? Why you have to select that one? So you have to compare. What? You have to compare. Okay. You have to compare the lightest angle, okay, because that is the cost. The heavier the element, the more expensive the element would become. That is logical, because if you are going to sell an scrap metal to a scrap metal buyer, the basis of pricing is the weight per kilo. Per kilo. Therefore, the lighter the metal, the more economical it would become, and therefore that is the most economical solution if you are going to compare. So compare them. Okay, you have to compare them. So this is the most economical solution. Okay, aside from being the least radius of gyration. So if you can compare these two, this is lesser, this two, this is also lesser. This is also lesser and also this one. So actually this is the second highest. Okay? But in terms of area, okay? In terms of area, this is the least area. And the least area meaning least amount of weight. Okay? The least amount of weight. So this is the most economical element. So we have to choose this. Okay? So that is the only thing different from previous chapter. Okay? So we have that criteria on how we choose the element. Okay? In terms of weight. Okay, what else? Built up members. So, meaning to say, the members is composed of a collection or connection or assembly of several parts. Okay? So, several basic parts. So, like for example, this assembly, okay? This assembly on the figure. Look at the figure. Okay. Okay. So, this is a built-up section. Okay. So, we have the C channel, but we have the plate. That's why it looks like, so it looks like a what? It looks like a hollow rectangular pipe, no? Hollow rectangular section because of this plate. Okay? So, it is now considered as built-up section. Again, I already mentioned we have the concept of slenderness ratio. Okay, slenderness ratio is dependent upon the direction axis for the y-axis, for x-axis, and also for radius of gyration. So you can say that Rx, okay, with this minimum value, you can take the slenderness ratio with respect to x. It is about this much. So we have 300. So there is a concept, okay, of this one, 300. Maximum preferable ratio is 300. Okay. So it is less than 300, therefore it is allowed. Okay. So that is another provision. That is a provision for design. Okay. So we have to check the slenderness ratio of the element. Okay. Okay, any question?
Oh, baka madali ka naman yung engineer. Atol. Ano?
Okay. So like this one. Maximum preferable. This is a code provision. Maximum preferable slenderness ratio is less than 300. This is the provision. So if you check, the answer would be less than 300. Okay? So next topic, rods and bars. Right? So you can design rods and bars by the same. This is the same. So this looks like the the what? This looks like the block shear, but now it is only equal to one part. It is not a combination of tension and shear. Only tension. It is only for tension. Okay? Because we have negligible shear because it is bars and rods. Okay? Negligible shear. So, only have what? Actually, not negligible. It has a maximum. It's a very great value for shear because it's very small and lengthy cable, for example, and the shear is almost impossible. Okay, shearing of that is almost impossible. So we only need to compute the what? The material resistance using this net tension, right? Net tension. So therefore, 0.75 is the phi, and omega is 2. So we can just what? Divide. Solving for the area, right? For the area. Okay, so solving for the area. Okay, now we have to solve for the area, and actually we have to solve for the diameter, not only the area. So after you found out the area, then solve for the diameter. Okay. Okay. So how to do that? This is an example, very easy. Starting with the load. Starting with the load, dead load, and live load. So we have LRFD combination, ASD combination. So find out the area for LRFD. So you have the following. The same formula. So you can notice the same formula. So then, after which you can now find out this RN actual using that actual area. Okay, so then now you can what find out the design strength. Okay, then compare with the given. Is the combination. You compare area so in the combination of load. This is the combination of load 44. Compare that to the capacity of material. Capacity is 48.6. Okay, it is okay. Therefore, what is okay? The size is okay. The size of the cable or the rod. Okay, the size is okay. Similar things happen again and again. The same concept. Even if you are using this type of offset rod, so you have to use the smaller diameter, not the diameter of the threaded portion, but the diameter of the smallest section, because that is the weakest link. This is the weakest link because smallest cross section. Okay, so they are being used as the cable, right? The cables or the rods and the bars on, for example, bridges like this. That is what? Suspension bridge. Okay. Another example, you are asked to what? Design sagrad, okay? Sagrad for purlins, okay? So this is what we mean by sagrad, okay? For purlins. Okay. So sagrads from this point going there and going there. This is the sagrad. Okay. So, how to design Sagrad, or the same what combination of load formula, then find out for LRFD, okay, and different thing for ASD. Now, component of loads parallel to roof surface, then load on top, inclined Sagrad, okay, so corresponding, okay. So component for first, how to do it? The slope must be the factor, then multiply by this. But you just have to multiply by the slope. As you can see on the picture, that is the slope. 1 over square root of 10, that is the 1 over square root of, that is sine. Okay, that is equal to sine. Okay, okay, that is sine, while the load of the Sagrad is 11 over 12. Okay, so what else? Details of Sagrad. So as you can see, this is the details of Sagrad. Okay. We have the inclined Sagrad here. Inclined Sagrad. This is the reds. So in the reds, we have the horizontal Sagrad. Okay. So these are the purlins. So these are the purlins. C channel. Purlins in the shape of C channel. So we are experiencing slow Wi-Fi. Very slow Wi-Fi. Okay. For example, Y here. Area of group used for computing the load for this Sagrad. So, why this area? This is the tributary area. Okay. You already know what do you mean by tributary area. That is from theory of the structure. So, this is the what? These are the purlins and these are the struts. Okay. So, tributary area of group. Okay, so another here, you can draw the tributary area here and another one here. So, meaning this part here are the support. Okay, these are the support. So, purlins are these lines. These lines are the purlins. Okay, so area is 7 times 37.9. We have the multiply by 11 over 12. Okay. Okay, so that is how we go through the procedure of finding out the size of Sagrad dimension, Sagrad design. Okay. Okay, so given here and this one, minimum size 5/8 inches. Okay, so assuming A36 type of steel. Pin connected members like this one. Okay, and the man I bar. So to be able for us to be, but to connect it to the plate, okay, to connect it to the static component, that is for tension members as available alternative connectors. So pin connected I bars. So we have this formula. This is a new formula, so a new concept. So we have what? The nominal tension force is equal to 2 TBE FU. Okay. So FU, we already know what it is, but you have to multiply that by TB. Okay. B is the width, and 2T is actually the T is the thickness. Okay. Like this one. Okay. So BE is equal to 2T plus 0.63. Okay. T is the plate thickness, but may not exceed the distance from the whole edge to the edge of the part measured perpendicular to the line of force. For example, letter A, B, C, D. So there are three different types of pin-connected tension members. Okay. So for letter A, tensile rupture. So definitely we have to multiply by effective area or the net area or the effective net area. Okay, so we have this formula. For shear rupture strength on effective area, so we have this following formula. 0.62T. Okay. For bearing strength, so 1.8 FYDT. So D is the diameter of the hole. Okay. So this is the rupture. So the rupturing is this area is the rupturing. So tensile rupture, shear rupture. Shear rupture, tensile. Usually it is what? Tensile rupture rather than shear rupture. Okay. So bearing and letter D, tension, tensile yielding. Tensile yielding, so width times T. So dt. Width is T. Width times T. Bearing is bearing on projected rectangular area behind bolt. Again, we have this. So those are new concept and new provision from the code. So there are corresponding 4 different formula. Okay. So while on this equation, we have again rupture. We have the rupture. So rupture is only this one. This is the rupture. Okay. So also this is another rupture, but this is tensile, this is shear. Okay. Okay, this is this is the formula for the same part here, because B is equal to 2T plus 0.63. Oh, this one. Oh. That's why we have this formula. Okay, empirical formula, we cannot derive it. So those are the code provisions. Fatigue loads, very important. Another failure mode, fatigue. So fatigue is a type of load that is dependent on the frequent variations and reversal of stress. Reversal meaning positive stress, negative stress, positive stress, negative. So those periodic changing of load, reversing positive, negative. That is what we mean by fatigue. That is the fatigue. Okay, so we have also the term stress range, and the fatigue life of members is what? Another concept, fatigue life. Okay, so the range at which the member life appears to be infinite. This range is called threshold fatigue stress range. Okay. It is anticipated that there will be fewer than 20,000 cycles of loading. Okay. Note that 3 cycles per day for 25 years equals 27,000 cycles. So if the number of cycles is greater than 20,000, allowable stress range is calculated in specified Appendix 3.3 of AISC. So 20,000. That is estimated to be 25 years. Okay. This is our main formula. So FSR, that is allowable stress range in KSI, kilo PSI. CF, what is CF? Constant from table. Let us take a look at CF. Then formula NSR is the number of stress range, fluctuations. Okay, number of stress range, fluctuations per day. Then FTH is the threshold allowable stress. If TH must be equal to or less than the FSR. Okay. So next section, PU. Well, it's equal to 192. Okay. So attention member is to consist of 12 section, W12 section, FY50 with PIIE 12, so welding. Service dead load 40K, And live load 20K, tension 90K, 50 times per day for estimated design life of 25 years. Select the section using the AISC procedure. 25 years. So we will see the we already know about this. We know this. So NSR. Ah? Oh. Oh. Okay, so NSR, number of stress range, fluctuations and design life. So we have the formula for that. So let us proceed. NSR is equal to 50, 365 times 25. So we have this formula. Number of stress range fluctuation per day times number of day per year times years of design life. Okay, so 25 years. How many fluctuations per year? Times 365. So 50 fluctuations per year, 365 days per year, 25 years. Okay, so that is our total NSR. Again, NSR, number of stress range fluctuation in design life. So, okay, so we have this formula. Okay. So again, we have CF from table. So we can take a look at table 3.1, appendix 3. Okay. So FTH 24 cases again from table. So therefore we can solve this one. 250 NSR. So we have this value. Okay. So we can take a look. This appendix table. Do I need to show you the table? That is on the appendix A of this PDF. Okay. So go and find this out from the table. And because of that, we have what? 37.84. 37.84. Okay. So actual stress must be less than. Of course, that is less than because 27.6 minus 4. That is 23.35. So that is less than FSR. Okay, so what? Minimum and maximum. Okay. Maximum service load, minimum service load. So those are from the formula. Okay, so take a look at this. And Appendix 3.3. So FTH, we have the threshold, maximum stress strain for the indefinite design life. Okay, another table in terms of KSI. Take a look. 40K, 90K, then that is 40K, 90K, that is actually what? This one, 20K, 90K. Okay. Surface load, 40K, dead load, 20K. Okay. 20K is compression, tension, 90K. So that is all live load. So combination of that, 20 to 90 with 40. So this is our tension load. So if you have the compression load, you have to subtract, because 40K is tension load, tension dead load, plus tension dead load, plus tension live load. So this is tension dead load minus compression live load. That's why we have to subtract. Okay. That is how we do it. 25 years, 50 times per day. So this is the estimated periodic changes in load variation. Okay, so that's why we have this 50. Okay, and then we have the element that we are going to use. Is the element that we are going to use. Gross area is 4.71. Why we can use this? Because this is more than the requirement. This is the requirement, 4.27. So we can use this material. How to determine? So there are several available elements. Then you can select using the most economical choice. But here you can check that out because it is given as W12 section. It is a requirement, W12. Okay. So we choose from W12 the most economical one. So by 12 by 16. Okay. And then the gross area, okay, pounds per square inch. So PSI, this is KSI, kilo. Okay. So load divided by area, that is tension load in KSI. Therefore, we found out that these are the answer. Okay. So for the problems for solution, practice these problems at the end of the chapter. You have to practice it. Okay, so there are several problems for practice. Okay, there are about 24 or 26. There are 26 problems. before we so we already discussed something, a small part of compression member. So maybe we can end our semester like this. We only able to describe compression and tension members. We are not complete with the compression members, but at least we initially have the lecture and some example, very short example. Unlike when we discuss the tension members, we have plenty of example and activities lecture. Anyway, we cannot do anything about it. You can ask your question. You can ask on our GC. Any question? Without a question, I would like to end our live stream right now. And please just wait for the message to be posted on our GC. Again, this is your professor, Dr. AP, teaching engineering for nation building.